Uh, in this section, we're going to talk about Christoffel symbols. Uh, in particular, we're going to prove the Christoffel symbols are directly related to the derivative of the metric. Okay. We introduced Christoffel symbol as a coefficient expansion of the derivative of the basis vector. In this section, we'll relate them to the first derivative of the metric tensor. This was also justified the identification of the symbol first defined in chapter 5. Remember, with that time we introduced Christoffel symbol simply as a set of first derivative of the metric. And now we show that they are the same thing. The expansion coefficient of the basis vector or the first derivative of the metric. We're going to show something that say the metric is covariant constant. Of course, the metric tensor is position dependent, so therefore the ordinary derivative of the metric is non-zero. However, we show if you differentiate instead of ordinary derivative, if you differentiate by the covariant derivative, it actually vanishes. So we say the metric g mu nu is covariantly constant. Okay, we can use the expression over and over again. It means that the covariant derivative, in this case, covariant derivative with the Christoffel symbol is equal to 0. Okay, we can prove this way. The metric is related to the basis vector, and I will apply the definition of Christoffel symbol to the derivative of the metric in this. So we take the derivative of this product of the basis vector. So differentiate the first one, holding the second fixed, holding the first one fixed, and differentiate the second one, and then apply the expression of Christoffel symbol as coefficient expansion of the derivative of the basis. We'll get this, and then we'll go back to the fact that this the product of the base vector is just a metric, so therefore this is the derivative of the metric, and this is Christoffel symbol, multiply the metric, move to the other side, get a minus sign, same way this. And you know this combination is precisely the combination for the covariant derivative of the metric, so therefore the fact that this equal to 0, so therefore the covariant derivative is equal to 0. As we see, the fact the metric is covariantly constant, or the covariant constancy of the metric, is a key property that allowed Einstein to introduce his cosmological constant into the GR field equations. Okay. So now we're going to show the Christoffel symbol are directly related to the derivative of the metric. Well, to do that, we first want to say the geometry we'll be working with has the property that the two covariant differentiations of a scalar function. You first differentiate to d nu, then d nu, then d mu, or d mu, d nu, the same. So therefore, this means these two derivative operations are commutative. Formally, we can easily show, in fact, it's an exercise to show that the Christoffel symbol must be symmetric with respect to the interchange of low indices. Gamma mu nu lambda equal to gamma mu lambda nu. You interchange the low indices, you get back yourself. Okay, this is very easy. You can show if this condition follows this, and then we can show what we want to prove is that Christoffel symbol is the first derivative of the metric, as we have given in chapter 5. In fact, this is called the fundamental theorem of Riemann geometry. The proof goes like this. Remember, we said metric is covariant constant, so I can write the covariant constant equation, but I can write it, repeat it 2 more times by cyclically permuting indices. Here's lambda mu nu, then I push the lambda over to lambda mu nu and lambda mu nu, cyclically permuted this way. And then, of course, the permuted the same way. They're all equal to 0. Okay. Now, if I add these 3 equations up, okay, and of course, they're still equal to 0, And but you can see this term, this is just this term was opposite sign, so cancel. These two terms cancel. Okay, so we're left with three derivative terms: this one, this one, this one, and also two gamma factors which are the same because the low indices are just interchange. Low indices doesn't do anything, so therefore these are the same. And then this, of course, this relation is just the relation we're looking for once you contract with the inverse metric. Okay, so this is how you prove the fact that this Christoffel symbol are related to the first derivative of the metric. Now, once we made the connection, the first derivative of the metric with the Christoffel symbol, we can better understand why we expect the metric to be covariant constant. Let's go to the local Euclidean frame. Remember, local Euclidean frame is the first derivative of the metric equals 0. So therefore, the Christoffel symbol vanishes in the covariant derivative. So therefore, ordinary derivatives equal to the covariant derivative because the difference is the Christoffel symbol, which vanishes in this coordinate frame. So this, the fact the first derivative vanishes, that's of course the flatness theorem. And this one replace the ordinary by the covariant derivative because Christoffel symbol vanishes in this frame. So therefore, we have covariant derivative of the metric equals 0. But now we only proven this in the local Euclidean frame, but because it's a covariant expression, when it's valid in one frame, it's valid in all frames. So therefore, we prove the fact in general, the covariant derivative of the metric is equal to 0. Then we'll ask you to do an exercise was given the fact the covariant derivative on scalar functions commute, and we can show that just write them out. You find that this implies that the Christoffel symbol, the symmetrics, but interchange the lower indices.